guess it's time that we start. It's my pleasure to welcome Professor Mahadevan back to Notre Dame. Maha is visiting us from Vanderbilt University. He has worked extensively actually on all aspects of the UQ problem, sensitivity analysis, desire ladder uncertainty, backward problem. He's also spent a lot of effort of educating people on reliability and UQ. A significant part of his work has always been connecting with industry and coming and see how verification and validation techniques can help create better products. And I think today's presentation is going to go along those lines. He has received actually a number of prestigious awards from different agencies. So let's all welcome Professor Mahadevan to Notre Dame.
Thank you, Alex. It's a pleasure to be here, especially to be talking to folks who are working in UQ already. So many times when I go and give seminars at different places, I have to give a lot of background information. But since you all are already working in this area, I can plunge right into the meat of the presentation. Well, I'll have to do it manually. Okay. So my current efforts are focused on some of these topics. Listed only the ones that I'm doing a major part of the leading the effort. There are a few others that I'm playing secondary role. So I'm going to be talking mostly on the first topic, model error quantification and uncertainty aggregation, which is largely funded by Sandia National Labs over many years. This second work on panel, hypersonic panels, UQ of those, this is funded by AFOSR, and then the additive manufacturing uncertainty quantification, uncertainty management, that's funded by NIST, and the Department of Energy has been funding health monitoring efforts, especially in concrete structures that I lead, and then I also collaborate with my colleague and one of your colleagues on piping corrosion health monitoring in nuclear power plants. Also extending the similar type of work to digital twins. I've been working with the Air Force on previous projects and now currently with the Army on developing digital twins for resilient operations of structural systems. The last two are more on the AI side, information fusion from multiple sources of data, mostly data-driven models on aviation safety and patient disease prognosis. Both are, but very different types of data availability. In the first case, I have very large amount of data. In this case, very sparse data. So we look at different ends of the spectrum in terms of developing machine learning models. So my focus today is mostly on the first topic on how do you quantify model errors and then and especially assess the model errors in predicting systems where you don't have information. For example, if you were to, just to give a background, if you were looking at modeling physical phenomena, first you have a conceptual model of that, and then which you translate into a mathematical model. And then you have a computer implementation of that mathematical model for solving. So you introduce broadly two types of errors. One is the model form error, and then the solution approximation errors, or the numerical errors. So the model form error, which appears in the governing equation of the model, there are, in the literature, there are two ways of assessing that. One is through the calibration technique, Bayesian calibration in particular, and the other is through validation techniques, so that you compare model prediction and observation, and then you make a statement about how valid the model is. And the numerical errors, solution approximation errors, are typically addressed using verification techniques. Now, before I go on to aggregation, I want to give you a motivating example. This is work that we have been performing with the Sandia National Labs. And in this case, this is the full-scale system. You have a red-colored, there's a mass which is covered by foam and sitting in a conical container with some joints at the bottom. And so the behavior of our quantity of interest is the acceleration, peak acceleration of this mass, and that is governed by the properties of the joints and the properties of the foam. So for various reasons, we cannot perform a full-scale, the test of the full-scale system. So what we have are tests at different levels, at the material level test, coupon level test, maybe component, subsystem, and so on. For example, here I have a foam with the two masses on either side, and I have a corresponding finite element model. And if I have the test and the model, I could perhaps estimate the foam properties through the model calibration, and also then estimate the model discrepancy. And similarly, on the joint side, I have a single joint that is modeled as well as tested, and then I can infer the joint properties. But then I also have data at a higher level, closer to the system of interest, where I have this mass encapsulated by foam, but of course the shape is very different from this. Again, I have a model and corresponding test data and some error terms. And similarly, on the joint side, I have a conical container, empty, without the mass and the foam. So I have all these different types of data at different levels of complexity of the system, but nothing that actually has the full-scale system tested or we have a model of the full-scale system, but we don't have test data to compare it against. So what we have to do is, based on the information that we have obtained from these lower levels of complexity, we have to be able to make a statement about how certain we are, or what is the uncertainty in our prediction regarding the behavior of the full-scale system. So that's the kind of one type of aggregation problem that I'm going to be talking about. So before we do that, I do want to mention this here. We have calibration and validation and verification, all that is going on at different levels. So you have all that information that is there. There is, of course, the aleatory and epistemic sources of uncertainty that are also coming into the picture that need to be properly aggregated. And also, super. Does it work?
It will now.
Okay, thank you so much. That's the. You also have, to consider the relevance of these different levels to the overall system, because obviously this test is probably a lot more relevant to the system than the single joint test. So how do you properly account for this relevance of the or closeness of the test to the actual application? Even though we're talking about relevance, there are similar issues that are also present in low fidelity versus high fidelity models. So there are some mathematical concepts that are kind of common to both types of situations. And finally, as I said, we want to predict the overall uncertainty in the system level behavior. So Bayesian calibration, I assume many of you have a good familiarity with through your research and classes and so on. So, and verification is the assessment of numerical errors such as discretization error and surrogate modeling error and so on. So I'm going to just quickly go over some preliminary remarks on model validation. There are many quantitative methods that have been proposed for assessing the validity of models, such as based on classical hypothesis testing or Bayesian hypothesis testing, basically where you compute the likelihood ratio. And those could be, the hypothesis can be formulated as equality or inequality hypotheses or interval hypotheses. Then there is a reliability-based method, which is basically a distance metric that we work on at Vanderbilt. There are also other methods such as area metric and, of course, Kullback-Leibler divergence, which assesses the information gain. In particular, I have interest in these two techniques, 2 and 3, because the model validation result tends to be a probabilistic measure, which I can more readily use in uncertainty aggregation as opposed to some of the other techniques. For example, if I was to use Bayesian hypothesis testing, the basic idea is that we are comparing two hypotheses, in this case, null hypothesis that the model agrees with the data, and alternate is that it doesn't. And then we would compute a validation metric, which is basically the likelihood ratio. We call it Bayes factor, which is the likelihood of observing the data given the null hypothesis versus the alternate hypothesis. This can also be then translated to a posterior probability of the null hypothesis that is supported by the data, which is if your prior hypothesis or prior probabilities of both the hypothesis was 0.5 and 0.5, then it translates to a nice simple formula, B over B plus 1. So as the Bayes factor increases, basically your so-called confidence in your model is also increasing. So that's why, so the result of the model validation is a probabilistic result. And similarly, if you have a distance metric that you can compute, what we have been referring to as the model reliability metric in a set of publications, in that case, you are simply assessing the distance between the prediction and the observation and computing the probability that it is less than some tolerance. And so that is also a probabilistic result of the validation, which I'm able to use in the aggregation, as I'll show in a minute. So then this is, of course, the probability of the alternate hypothesis. So given this background, so now let's see how I might go about aggregating and propagating results from calibration, verification, and validation. So if I do verification, basically I'm trying to assess the numerical errors in the solution process, such as discretization error or error due to reduced order modeling or surrogate modeling. In that case, typically the computation tends to be expensive in terms of calculating. If you were doing a discretization error assessment, for example, you would use something like a Richardson extrapolation or something like that. So you have to run many runs of the expensive physics model, so it tends to be expensive. So you do have a limited amount of data to assess the numerical error. So you end up actually having an uncertain assessment of that. So you end up showing a density function, either prior and posterior or so on, of the solution errors. So you have the PDFs of those. Or you might have a deterministic estimate, in which case you would correct the numerical prediction before you go on to do calibration validation. So the calibration, of course, is giving you also a PDF, a posterior PDF of the unknown parameters, model parameters you are calibrating. The validation data, as I mentioned in the previous slide, you might be able to compute a probabilistic metric of validation. So now if I want to take all this information to the system level prediction, there might be two types of situations that you would like to address. One is that, for example, I have this lower level model and the corresponding data. The superscript C and V refer to calibration and validation data. So I could, for example, X1 is the input and theta 1 is the parameter for this first model, and Y1 is the output, and I have corresponding calibration validation data, and similarly for this other model. And maybe the outputs of these models are then input to another model which computes, let's say, a system level quantity. In that case, you have a sequential relationship between lower level models and the upper level model. In that case, what we do is, of course, we have, let's say, using some calibration data, we have computed the posteriors of the parameters, which also includes posteriors of the discrepancy terms. And then you also have model validation of the prediction. So what we will do then, going forward to Z, is something like this. So I have the model prediction, which is, let's say, and then you have your, this is the based on the null hypothesis, and then you have the validation of that. And then you have the alternate hypothesis prediction, which could be just a simple expert opinion of some range of values. It could be as simple as that. And then you have the model unreliability value. So you could simply do a Bayesian model averaging of the prior and the posterior prediction and the corresponding confidence, and then aggregate them towards propagation to the next level. That's one way of sequential aggregation. Another way is, this is also quite often the case. In fact, the one that I showed you before was this case where I have maybe modeling and testing at one level, and then modeling and testing at maybe a higher level of complexity. And then, so the question is, how do I assess the posterior distribution of theta that I should use for my system level predictions? So in that case, if I have, let's say, from one level, I could do something like this. I can take the posterior from the calibration, and then multiply that by the validity of the model, because you remember, the posterior of your calibration, of course, depends on what model you used for the calibration. So it is going to be affected by the model. So we multiply the posterior by the model reliability, and then the prior by the model unreliability. So another type of Bayesian model averaging on the parameter that is being used in the system level prediction. So there are two ways to think about this aggregation, or what we call roll-up, as the information goes from lower level complexity to your full-scale system. And this, of course, for a single level, and you can expand this for multiple levels. For example, if I have two levels, I can think of, can develop formulas like this, where I have data at both levels. Then the first term, in fact, is the posterior using both types of data, and then the corresponding model validity result. And then the second term means that this is the posterior using only the second level data, and that means that I believe the second model, but I don't believe the first model. So probabilities of that, and vice versa. I trust this first one, but not the second one. And then if I don't trust both, that's the last term, which means I only use the prior. If I don't trust any of the two levels of data of the models, then all I have is just the prior. So there are these four possibilities and the corresponding probabilities of those, so you can develop a aggregation strategy like this. Further, as I mentioned, you also want to think about relevance of each of these pieces of information to your prediction. Oh, I should have mentioned something here. If you look at this here, if this is the green is the prior, and then I have the posterior based on just a single levels of model and the data. And then when I combine both, I have this posterior. So the question is, which of these posteriors should I believe? And that is what is addressed by this formula, where I also look at the validity of the models at each of these levels before I decide which posteriors or how much weight to give to these different possible posteriors. But if I also bring in the relevance, then how to do that? So there may be many ways of thinking about relevance based on either physical arguments and so on. So we have pursued using sensitivity analysis. We basically compare the sensitivity of the level at which you got the data and the sensitivity of the level at which you're doing prediction, and we compare the two sensitivity vectors for the same parameters. So the sensitivity vectors, what we do is that this is the sensitivity vector at level I, and this is the sensitivity vector at S. These are, of course, variance-based, Sobol index-based sensitivity vectors. And so then we combine these two to come up with the relevance index, which is basically a dot product of the two vectors. And then we can bring that sensitivity also, because if that sensitivity vector or sensitivity index is something that is a quantity that goes from 0 to 1, then it can be treated like a probability using the Cox theorem. So then you can extend the formula that you had before by also including the relevance metrics into this formula, something like this, where you have, for example, the first term means that both models are good and relevant, whereas in these other cases, you have different combinations. Maybe the model is good, but it's not relevant, or maybe it's bad, but it's relevant. So you have probabilities associated with all of these different events, and you combine them all in this rollup. So for example, if this is my prior, and let's say I had the posterior, which was based on the previous approach where I didn't consider relevance, I get a pretty sharp posterior. But now, if I also bring in the relevance, obviously, you should think about it like this. The lower level data, for example, at the coupon level, of course, the modeling is a lot more accurate. So your model has usually very high reliability. And because it's a simple enough experiment, it might be nice to control and get very high accuracy in the data as well. So you might actually get a very sharp result, but then its relevance to the actual system is not very high. So what happens is then this sharp posterior gets modulated or expanded to account for this lack of relevance of the very highly accurate data. So you want to consider both accuracy and relevance of the different sources of information in your aggregation. So this is one stream of aggregation where you have models and data and different activities, calibration, verification, validation at different levels, and you are pulling them all together to assess the uncertainty in the system. Another type of aggregation that we often have to do is the fact that you have both aleatory and epistemic sources of uncertainty propagating through your models. So for example, if you take the simple case of input going through this model to this output, you have aleatory uncertainty, let's say natural variability in your model input, X, but then you may not have enough data to actually precisely characterize that variability through probability distribution. There might be uncertainty regarding the distribution type and the distribution parameters and even correlations between those model inputs, right? So you have that epistemic uncertainty. So in the presence of that, what you have perhaps multiple competing distributions for your model input, right? With different distribution types and perhaps different distribution parameters, values. You also have, of course, uncertainty in the model itself, which can be broadly characterized by the model parameters and then the model errors. So even for a fixed deterministic value of the input, because of the model uncertainty, you have a uncertain output. So you have these source of epistemic uncertainty. So a lot of the work in the early years of uncertainty analysis was mostly about propagating variabilities through Monte Carlo simulation and a forward propagation of uncertainties. But of course, in the last 2 decades, there's been a lot more awareness of epistemic uncertainty and inference and inverse problem as part of the, in fact, that's what, in my opinion, characterizes UQ as opposed to the previous generation of uncertainty analysis methods. So when you try to aggregate and also assess the relative contributions of different types of uncertainty sources. One way is to do nested approach, where you have some realization of these distribution parameters, and then you propagate that and so on. You can do it in a nested way, but it tends to be very expensive. And it's only a qualitative assessment like this, but you don't really have an idea of how much is the contribution of the different sources. So what we have pursued in our group is introducing the concept of auxiliary variables, which are then able to complement if you have aleatory, then epistemic, and so on. And therefore, we are able to use that for sensitivity analysis and assess the relative contributions. For example, let me quickly go over that. So the auxiliary variable approach, so you have two situations where you have, for example, if the uncertainty, because of the inadequate data, you have some uncertain distribution parameter, for example. For a given value of the distribution parameter, you have one distribution. If the value of p changes, you have another distribution. So there is a stochastic mapping, so there is a one-to-many mapping here. Similarly, you have, in the case of model uncertainty, there is a stochastic mapping because of the uncertainty. So in both cases, you have stochastic mapping. For things like what we do, Monte Carlo simulation, reliability analysis, sensitivity analysis, what you really need is a deterministic model so that you can, for a given value of the input, you get a particular value of the output, and then using those results, you can assess things like reliability and sensitivity and so on. So how to do that, we would introduce an auxiliary variable, which is just uniformly distributed between 0 and 1. It's nothing but the probability transformation, integral transform, where U is simply the CDF of this distribution, conditional distribution for a given value of the parameter. So, in fact, this is exactly what we do in Monte Carlo simulation, where let's say you have the value of the distribution parameter, and then you choose generate a random number value between 0 and 1, and that gives you a unique value of x, right? So this is now a one-to-one mapping. So, and this is the transfer function. So this is not anything fundamentally new, because this is what we do in Monte Carlo sampling all the time. But explicitly, but once we do the simulations, we don't really keep track of the auxiliary variable u. But if you explicitly keep track of it, we've found that it gives us some advantages. Once I have this here like this, in this case, p is the distribution parameter, so that is the epistemic uncertainty, is a measure of epistemic uncertainty, and u, which is looking at the CDF, is a measure of the aleatory uncertainty. On the other hand, if I were to use this example, then x is the measure of the aleatory uncertainty, and the corresponding u that would refer to the model uncertainty would be the epistemic part. So I'm able to use this idea of auxiliary variable in both cases. And therefore, I will have a one-to-one input to output relationship, which I can then use for reliability analysis. And I can also, even more importantly, use for global sensitivity analysis, where I can introduce auxiliary variables and have a one-to-one relationship, and then compute the, let's say, Sobol indices or something. So in that case, the uncertainty aggregation flow would be, it's a little busy, but main idea is that I would have the distribution parameters, distribution types, and sample, and also the corresponding auxiliary variable sample, so I get a unique sample of this. And so I get samples of the input going into the model, and similarly, I have the inputs that are aleatory. Then going from input to the output, I have these model errors, which are epistemic. Again, I would introduce auxiliary variables for those, and I'll be able to get a unique value of y. And then I have the entire aggregation flow from input to the output in a one-to-one mapping. So, for example, if I were to do global sensitivity analysis using that, this framework, then basically what I will do is I will introduce auxiliary variables. First of all, for the input epistemic uncertainty, I have an auxiliary variable. Similarly, I have auxiliary variables for model form error, the discretization error, and then the surrogate model error if I have a surrogate model, and so on. And so I'm able to track it all the way down to a unique output for unique values of each of these. And then I can calculate these Sobol indices, which will then tell me how much is the contribution of, let's say, natural variability in the input versus the data uncertainty versus this model error term or that uncertain parameter. So I have the entire assessment of different uncertainty sources contributing to the overall uncertainty in the output. So a very simple idea of this auxiliary variable seems to be giving us a very powerful ability to assess, because this is important. Because if you assess the contribution of different sources of uncertainty to your overall prediction uncertainty, then you can direct resources for example, if it is epistemic uncertainty, you can direct resources to reduce that epistemic uncertainty, such as maybe refining your model or collecting more data and so on. If it is aleatory variability, which is irreducible by definition, then just investing more resources is not going to help you. So this will help you to assess how to allocate your resources in an effective manner for uncertainty reduction. So just on the side, there are also these SOBA indices calculation tends to be, in many cases, double loop sampling, especially when you have correlated variables. So we have done some additional work on simplifying that or making it more efficient using basically converting it to single loop samples where you have, based on stratification of the space, we calculate those indices in these segments and then average them out, and also extend it further using important sampling kernels. I'm not getting into that because I want to stay with the main theme of uncertainty aggregation. We extended further to Bayesian networks where you have aggregation of multiple components and sources. We have used this idea for dimension reduction, of course, based on sensitivity, but also for seeing which of the parameters are sensitive to the data. So using that to test, design, and select various kinds of tests. In fact, one powerful application that we were able to leverage this was in this digital twin work that we did for Air Force Research Lab on the Airframe, where you have a dynamic Bayesian network that represents the evolution of uncertainty in various parameters and state variables in the system, and using multiple models and data sources such as inspection data and onboard data and so on. So I'll give you a simple example of an aircraft wing, and let's say you have a crack at this location, and of course this is a simple model, a simple network, but for an actual realistic wing, you have a network with hundreds of nodes at each time instant. So what we had to do using the global sensitivity analysis that I just mentioned, we used that to reduce our dimension. And also the Bayesian network, in general, we would use particle filter to propagate the uncertainty across time. Or you can use Kalman filters if you can get away with some Gaussian assumptions. So what we ended up doing was we partitioned the network into Gaussian and non-Gaussian portions and used Kalman filter for the uncentered Kalman filter for the Gaussian portion and so on. So we were able to take all this to scale something that took 10 hours to 1 second. So the same idea when it was applied to an aircraft wing for demonstration. This work was led by GE and Lockheed and Vanderbilt were the two other partners. And we developed this dynamic Bayesian network approach and the scaling. So the whole thing took only 15 minutes for information fusion. With all the high fidelity Vanderbilt model coming in, and then the inspection and various types of data coming in. And so you are now approaching real-time decision-making capabilities for a Army commander, where you are able to track the uncertainty in this case it was crack growth, and of course as you are predicting into the future, you have the uncertainty that is growing. When you have inspection, the uncertainty reduces and again it grows, and so you're able to track the uncertainty and then therefore decide. In this case, it was the application was sustainment of the aircraft. So when do I do inspection? When do I do repair, maintenance, and so on? So by being able to track the uncertainty over time using, and of course, the first concern that we had when we began the project was, are all these methods scalable? And that's what we achieved through this various types of efficiencies in this process. So, and we are currently working on the same idea of digital twin, but not for inspection or sustainment, but more for resilient operations. This is funded by the Army Research Lab, where you have the helicopter, various types of maneuvers will give you different types of loads on the helicopter, and then you have sensors that are sensing the damage, and so we do probabilistic diagnosis and prognosis, and then use that to identify what type of maneuvers am I allowed to do so that the damage doesn't grow too much before the mission is complete, so that we can complete the mission safely by using the most up-to-date information about the system health and capability. So these are some further benefits of the kind of uncertainty aggregation that we have laid out so far. However, all that I have talked about so far has used, by and large, of course, I talked about particle filter and state estimation to some extent, but in terms of the main engine of Bayesian computation, it was all based on parameter estimation, which is Markov chain Monte Carlo methods, and so on. So to compute the model parameters and then the model discrepancy, typically using some kind of approach like this, a Kennedy-O'Hagan approach, where you have the model output, and then you have the data, and then you have the observation error, and then the model discrepancy. Typically, this is the framework in which you are estimating the model parameters and then the discrepancy term. Of course, the discrepancy term, you can have multiple formulations, such as you may completely ignore it, or you might have a constant or some Gaussian variables. Of course, if you're measuring at different points, you might have different Gaussian variables at different locations with mean and variance fixed, or input dependent. You can also model that as a stationary or non-stationary Gaussian processes. So there are many different options for modeling your discrepancy terms, and depending on how you model the discrepancy term, you're going to get different solutions for your parameter estimation. And of course, the more sophisticated your representation, the more accurate it might be in the mean, but then you might have a large uncertainty, because given a fixed amount of data, the more parameters you introduce, there's going to be a lot more diffused estimation. So there is a challenge that there is a computational effort versus accuracy versus uncertainty. All that has to be balanced in doing so. But the point that I want to stress here is that this type of approach that has largely been followed in the literature can only estimate discrepancy at the level of the model output, model response. So you're comparing the model output to observation, and you are estimating the apportioning that difference to partly to your model parameters and partly to a discrepancy term. This is what you're doing. It doesn't say anything about how much, now if I want to predict for a situation where I have not tested, what's the discrepancy? This discrepancy term cannot go there. So this is just applicable to the test situation. So the discrepancy term does not travel. The model parameters will travel. So therefore, you have some information that is not available at the prediction level for an untested system. Or even for the same system, if you have responses or locations that are unmeasured, this discrepancy cannot travel. The discrepancy is only applied to that particular quantity measured at that particular location, right? So it's a very, very restrictive way, especially if you're looking at extrapolation or dynamic systems. The other thing is, we are only quantifying this model discrepancy at the level of the output. We are not saying anything about the model form, the governing equation of the model. which is really what we want, because if you want to extrapolate, as long as the governing equation is the same, the boundary conditions, geometry might be different, but if you're using the same governing differential equation, you want to be able to go to the source and identify the error in the governing equation. Then you could take the corrected governing equation to a prediction situation. And of course, this is also a challenge where the discrepancy is accumulating with time in dynamic systems, whereas this has been mostly applied to static cases or instantaneous discrepancy at different time instants. So these are some of the limitations of this Bayesian parameter estimation type approaches. So whatever I discussed before in terms of uncertainty aggregation, though, that would fall under this class of what I call indirect approaches, where I'm going from calibration to prediction. If I had the same configuration and same quantity of interest, then perhaps I can try different inputs, find the discrepancies. I can create a surrogate for the discrepancy and perhaps do that. We explored that for some air cycle machine type applications. But if the configuration changes, boundary condition changes, or the quantity of interest changes, you cannot use this discrepancy term for anything. So one indirect approach that has been pursued by folks at Sandia is that perhaps instead of making that discrepancy term as additive outside of the model prediction, bring that discrepancy along with the model parameter theta. So this is referred to as an embedded discrepancy approach. So then you are expanding the model parameter distribution by accounting for the discrepancy and then using this in your prediction. So I mean that is this, of course, discrepancy term has some parameters, so it is no different from just parameter estimation. It just happens to be inside the model. What I presented before in terms of combining, taking the data in the embedded discrepancy approach, of course, all of the data is just treated as calibration data. Whereas in this approach, we partition the data into calibration and validation data, and then we do this Bayesian model averaging, which I mentioned earlier. Which can then, of course, the advantage of this approach is that you can go up across multiple levels of data, including relevance, whereas the embedded discrepancy is still not able to address these, at least as far as it's reported so far. So these are all indirect approaches. So what I want to focus on is a direct approach. So I want to make a key distinction. I've written a lot of words here, but this is really the most important thing here, where I'm going to distinguish between discrepancy, which is at the level of the output, the model output, compared to the response, true response, as opposed to model form error, which is the error in the governing equation. And if I'm able to catch that, I might be able to do extrapolation much more meaningfully. So in order to do that, I go back to Bayesian state estimation, where of course, the Bayesian state estimation, you have two steps. Many of you might have studied that in your classes. So you have the prediction step based on the current model, and which is given by this equation. You have the prediction of xk given the state variable x at k, given the state at k minus 1, and you have the data. So this is the xk given all the observed data y up to k minus 1. So you have this prediction. And then you have the updating. Now you have observed the data at y at kth instant, and then you have this updating using the straightforward Bayesian updating. So you have this prediction and updating that's going on in state estimation. So you can numerically implement that using the particle filter approach. But if you can make Gaussian assumptions, then you can implement Kalman filter or other variations of Kalman filter. So that's the basic background of Bayesian state estimation. So how would I use that here? So suppose I have, let's say, two articles A and B. I have done experiments on A, but not on B. Okay. They have some common properties. They have similar physics, so I can use the same governing differential equation. And they have common parameters. Maybe they are made of the same material and so on. But they have different geometry and maybe different boundary conditions. So the question is, can I use the experiments conducted on A to infer the response of B? So the way to do that is, first, I will estimate the model, not the discrepancy, but the model form errors using the tests in A. And I'm going to represent the model form error as an additional term in the governing differential equation, as an additional force term. And this is, of course, done element by element. So in the context of finite elements, you will have a discretized model form, governing equation at the element level. So this is repeats for each of these elements. And then I would build a surrogate model that connects the system state to the model form error. So this, of course, there are many options available for surrogate modeling. So then, for the prediction condition, this for this configuration B, what I would do is then, in this case, I have the model which predicts the states, and then use the surrogate model to bring in the discrepancy term and add that, and then assess the uncertainty. So that's the extrapolation which goes to the, it makes use of the model form error, which is at the source. So as long as the same governing differential equation applies, I can take it that way. But if you just stop at discrepancy, you won't be able to do anything with that. So you need to go back to the source. The one caveat is this works fine for all the interior elements, but at the boundary, if the boundary conditions are different, then you will have a challenge. But you are still much better off than before in terms of using the parameter estimation. So if you use state estimation so you would estimate the states, and not only the states that were measured, but also all the unmeasured or the latent states. And then you will use one more step to estimate all the model form errors, which are also considered as states. And once you do the state estimation, then you do the surrogate model to connect the states to the model form errors. So we have applied this idea to multiple types of applications. For example, airfoil under hypersonic flow. And then, so here you have, for example, flat plate data, and then you have curved plate you want to predict. Air cycle machine for a nonlinear multi-component system. And also, this is a dynamics challenge problems developed at Sandia. So we have applied this. So I'm just going to give you, I see that I'm running out of time. For the hypersonic panel example, you actually have four disciplinary models: aerodynamic heating and heat transfer, structural deformation, and aerodynamic pressure. So these are coupled models and evolving in time. So we want to, and there are model errors in different models. So you want to assess those model form errors, and then use that for propagating. Given the time, I'm going to skip that to just show you that the for the example that I'm conducting, so we are finding some very good results using the state estimation approach, where our actual true value and the estimated discrepancies are almost the same or close to each other. But there's one last thing I want to say about this. This type of approach, this Bayesian state estimation, in order to assess model form errors, requires two things. One is altering the system model, because you're going to go in and add an additional force term in the governing equation. And so you have to have access to the governing equation. That's not going to be the case in many situations. And the second thing is you have to interrupt the simulation and do the update, all this model form error and then the system states, and then restart the simulation. So you have to do two things: alter the governing equation and also stop and start the system model. Neither of those are practical in most realistic situations. So therefore, what we have, if you have a completely black box or non-intrusive situation, then all you can do is parameter estimation. You cannot do state estimation. If you have semi-intrusive, where perhaps I don't have access to the governing equation, but I can interrupt the program, stop and start, then I can use that for at least estimate the discrepancy at each time instant. That's about all I can do. But if I have fully intrusive, like I said before, then I can, of course, model form errors and all those things I can do. So what we have done more recently is that we have developed a semi-intrusive approach that can achieve the same thing as a fully intrusive approach, meaning I can stop and start. So adding a discrepancy term. So how does this work? What I have done here is that suppose this is your governing equation, and then if I were to represent that using time integration, that looks like this. So then I do a first order or second order Taylor series approximation of that. So then I'm able to collect all these terms into something. This is your actual prediction model, and then I have these error terms. The only thing that I need is this derivative, which is approximated by the derivative that you get at the model, with the model you have, which is not exactly rigorously correct, but it's an approximation. If I'm able to do that based on a second order Taylor series approximation, then I'm able to estimate that discrepancy corrective term in the system model and use that with the, of course, appropriate prior assumptions for the discrepancy term. And because you remember, semi-intrusive only works with the discrepancies instantaneously, so I'm working with discrepancy. But then relating that discrepancy back to the model form error using the second order Taylor series approximation. And then once I have the model form errors, like before, I create a surrogate model of states versus model form errors, and then I use that to, again, recalculate the states and start the next time instant and so on. So I have to do this. This is a semi-intrusive approach where I use a second order Taylor series approximation to achieve the model form error calculation. And if it is completely, for example, it's a Timoshenko beam, this is a Timoshenko beam, but then I'm assuming it as an Euler-Bernoulli beam, so I am obviously, there is a model form error. And you have also, the test is done at different lengths and with different loads. Prediction is at different loads and different lengths and so on. And I find that this approach that I just mentioned, if I do fully intrusive versus semi-intrusive, it seems to give an excellent result for this, of course, fairly simple problem. And if it is completely black box model, then what we will do is to convert the non-intrusive into a semi-intrusive, which means what I will do is basically create a surrogate model of this black box model, and then use that surrogate model in a semi-intrusive manner and do the same thing as before. So the kind of surrogate model, of course, now we are talking about a dynamic system. You have lots of states at every time instant. States meaning the deformation, stresses, whatever, at every node in your model. So it's a very high dimensional input and very high dimensional output. So typically you have to do some kind of dimension reduction. So for the outputs, we take the principal components analysis and reduce the dimension. For the inputs, we use the active subspace discovery, basically, which is a PCA applied on the matrix of derivatives, so to speak. And use that to develop a small set of surrogate models. And there are many different approaches that we are pursuing. For example, a autoregressive model, or we've been improving that with the recursive neural networks and so on in recent days. And so we develop a surrogate model and then use that surrogate model in a semi-intrusive manner for discrepancy prediction. So we tested that with this Timoshenko beam, and you can see the it's hard for you to see from there, but the non-intrusive is slightly off compared to the semi-intrusive, as you might expect, because the non-intrusive is also introducing some errors due to the surrogate model. So there is an additional error that is coming. But still, performance is extremely good compared to the computational cost. And we took this Timoshenko beam and did one further step, where we have not only the model form error due to Euler-Bernoulli assumption, but also, let's say it is being heated and the governing differential equation did not consider the deformation due to this temperature. So when we did this problem also, we were able to see that the non-intrusive case was performing almost as good as the semi-intrusive case, except a few as expected errors. But the errors were still, we are talking of the order of 0.01% difference and so on. So to conclude, the non-intrusive approach does introduce additional errors due to surrogate model. And then when we are assessing the model form, this is a key point. Of course, we don't really, we can, but in this case we did not. You can quantify the surrogate model error and then separate it out. If you don't, then of course your model form error will include the contribution of the surrogate model error. So you may want to guard against that. But it does simplify the system model based on this dimension reduction, and that helps us to reduce the number of parameters to estimate, and therefore increases the accuracy or the estimates. It reduces the uncertainty in the estimates. So to summarize, what I have presented is Bayesian approaches for uncertainty aggregation in two cases. One is the aggregation of model calibration and verification validation results up the chain of complexity. And second is the assessment of relative contributions of aleatory and epistemic source of uncertainty using auxiliary variable type approach. But if I want to actually do extrapolation, then I need to go all the way back to the governing equation and estimate a model form error and use that to estimate the discrepancy in prediction for the untested system. And so to make this more scalable, we have developed semi-intrusive and non-intrusive approaches. And we have demonstrated this for single and two disciplinary, actually this I should correct, for a four disciplinary model. That hypersonic vehicle panel have four models. So that's the end of my presentation. Thank you for your attention, and I'll be happy to take any questions.
Actually, we're exactly on time, but we can stay a few more minutes for any questions from the audience. Sam?
How much efficiency you get by using this auxiliary variable?
Yeah.
Because we have that problem with fluid structure interaction. You get aleatory and your inflow and then your modeling errors.
Yeah.
And we use typically nested approach.
Yeah.
But if this speeds up quite a bit, then I think we should look into it.
It does speed up quite a lot. Of course, it depends on how much effort you invested in the nested approach. For example, in the paper that I would be happy to send you, we actually show a comparison between the nested approach, and we are talking about the order of efficiency improvement, like order of 3 or 4, 10 to the power 3, 10 to the power 4 in terms of factor number of simulations reduced. Yeah. So it is a significant gain. But more than the computational efficiency, you're also able to assess which sources of uncertainty are more dominant, and therefore you're also able to reduce your dimension of the problem and allocate resources properly. So that, I think that advantage is probably even bigger than just the computational advantage. But computational advantage is also very significant.
If you can control the aleatory, you already know that there's no need to spend too much effort there.
Correct, exactly. Exactly. Yeah. Other questions? Yeah.
In the example where you use the model form error on plate A and then you move it to B, you said you can't use it on the boundary. What's the?
Yeah. So so when you cannot translate on the boundary, then you are restricted to what you did before, which is just you have the uncertainty in the parameters that propagates, but the uncertainty in the model form error, I mean, you will still do it, it just won't be capturing everything.
Okay.
So we found that in the boundary, we were only capturing partially the uncertainty, whereas interior, we were able to capture fully. Yes,
Okay.
so at least you are getting a partial improvement over previously what you could do. Yeah.
Okay, any other questions? Let's thank Maha again.